So this particular relationship between 3 units, 4 units and 5 units that forms a right angle is really fascinating, and it's been used a lot to measure right angles. So we can say that 3, 4 and 5, the lengths must have a right angle. But we can also say if we have 3 units on one side, 5 units on the other, and the distance between those 2 corners is 5 units, that must be a right angle. So if we took a length of 3 plus 5 plus 4, you would get 12. So if you had a 12 centimetre rope, and you divided it into 3 centimetres, put a knot, 4 centimetres, put a knot, and then you had 5 centimetres left over. If you wanted to check your building or your land that you were measuring was in fact the sides met at a right angle, what you would do is you would run your 3 centimetres down one corner, run your 4 centimetres down the other corner, and if this other piece of rope here met at this corner, you would know that you had to have a right angle. So it could actually be used, this concept of 3, 4, 5, to check to see if you had right angles on a building you might have been doing in ancient times. So it was actually quite a useful piece of knowledge that could be used in navigating land and surveying land and making sure your buildings were actually square at the corners. Right, so let's have a look at some of the other things that we can do with triangles. So could you draw yourself a 3, 4, 5 triangle? So you can do this too, and grid books are definitely the best to be using. So let's look at the base of 4. Can you make a little square at the bottom of that base? So that's 4. Measure down 4 as well. So it's very easy to do on grid paper. And measure down 4. Keep it really square. So measuring down 4 on the other side. And now I have a square, which is 4 by 4. So it's 4 by 4. So if I draw my 4 by 4 centimetres squares now. So drawing those so you can see it's a 4 by 4 square, 4 times 4. How many little squares am I drawing if I divide it into 1 centimetre squares? 4 times 4 is 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There's 16 squares there. Okay, so there's 16. Now I do the same thing here, except because this is 3 centimetres long, I'm going to draw a 3 centimetre square. So each side length is 3 centimetres. And I divide it into centimetre squares, like so. And how many little squares would I have inside that square which I've drawn? Well, 3 times 3 is 9. It's a square number. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So I've got 9 there. So what would happen here if I actually divided, and it's not so easy on a diagonal, it's better if you've got a set square to keep this accurate, but I'm just going to be a bit sneaky with my ruler. So I'm going to draw here, being sneaky with my ruler, using the fact that I hope it's at right angles, and measure, see how accurate I've been. Up here, 5 centimetres, mark them off. I'll check this is 5 centimetres. Yes, I've been really accurate. So along here, mark these off. 1, 2, 3, 4, 5. And now do the same on the other sides. I'm hoping you can see this, just making sure it's in your vision. So measure the 5 centimetres along the diagonal side, which we call the hypotenuse, and also along here. Join it and measure off my squares. So now I can join them. So I have got how many little squares? How many centimetre squares is this one going to be with the side length 5? So 5 times 5 is a square number. I think we all know that 5 times 5 is 25. I'm trying to keep this as accurate as I can, but it's not perfect, and I'm aware of that. So 5 times 5 is 25. Okay, so we have 16 here, 16 centimetres squared. We have 9 centimetres squared, and here we have 25 centimetres squared. So what happens if I add the 16 and the 9 together? What do I get? I get 25. So 4 squared plus 3 squared equals 5 squared. So we can write this as, with the side lengths, 3 squared plus 4 squared equals 5 squared. 9 plus 16 equals 25. Well, is that a coincidence? Is it a coincidence that the two shorter sides of the triangles squared, so the short side 3 and the short side 4, 3 squared plus 4 squared is 5 squared. Is that a coincidence? Well, it's not a coincidence. It's actually called the Pythagorean theorem, and we've just demonstrated the Pythagorean theorem. In fact, the two shorter sides, if you square the two shorter sides of any right-angled triangle and add them together, you will get the square of the longest side of a right-angled triangle. So this longest side of the triangle has a really important name, and it's called the hypotenuse. And it's a pretty crazy name, really, isn't it? So it's HYPOTENUSE, the hypotenuse. And it's always the longest side of the triangle, and it's always opposite the right angle. So you can always tell the hypotenuse in a right angle triangle because it's the longest side and it's opposite the right angle.